We will now take a close look at TeraData's architecture, which enables it to handle very large-scale analytics tasks and process them efficiently. We begin with a look at the concept of symmetric multiprocessing. This is also known as shared memory multiprocessing, and this is a setup involving multiple processors, and these may be scattered across multiple machines, but significantly, each processor is treated exactly the same way. So while the processors may not be exactly the same, they will be treated as such. All CPUs have access to the same shared memory as well as I/O devices, so symmetry is assumed in this regard as well. And as you may have guessed, the hardware which is used to support TeraData Vantage is based on symmetric multiprocessing. So in short, each CPU is just as likely as any other in the system to be assigned a particular task. Then there is the concept of massively parallel processing, or MPP, and this is where the SMP hardware is simply linked together with a communications network. So we may have hardware which is dispersed even across geographical locations, but they're all still connected. And this connection is made possible by something called a binet network. This includes a lot of the standard networking features such as broadcasting, multicasting, and point-to-point communication of messages. And with that, let's move over to the different layers and components which make up the architecture of TeraData Vantage. Clearly, there are many different pieces in here, so let's focus on some of the important ones one at a time, starting with the advanced SQL engine, which we have already touched upon previously. So Teradata, of course, is not just a database. It is a single platform which combines features of a database as well as the analytics capabilities of a warehouse. And it is the analytics capabilities that are enabled by the advanced SQL engine. This not only allows SQL queries to be executed in the most efficient manner, it also supplies various functions that are not part of standard SQL. And much of these functions are to do with advanced statistics and machine learning. Heading back then to the architecture diagram, another important component is the native object store, which adds to the flexibility of TeraData Vantage. There may be many occasions where the data which currently resides in an external platform will need to be analyzed, and with most analytics tools, this will require a migration of the data into the platform. This, of course, can prove very tedious and time consuming, and beyond that, it is often a temporary measure since the data will often be removed right after analysis is performed. To avoid going through the trouble of migrating the data in and then removing it, TeraData Vantage's native object store allows us to directly operate on the external data. So we can leverage all of the analytics capabilities of TeraData Vantage without having to perform any migration. There are, of course, some limitations. The native object store only supports CSV, JSON, and Parquet files that are stored on S3 compatible platforms. Specific examples of such platforms include Amazon's S3, Google's Cloud Storage, Microsoft Azure's Blob Storage, and the NetApp Storage Grid. Another important aspect to keep in mind is that TeraData Vantage can be scaled quite easily. The nodes in the binet are loosely coupled, which means that adding and removing of nodes is quite painless, which also translates to the fact that Vantage can be scaled to thousands of physical CPUs, which in turn are broken up into tens of thousands of virtual CPUs, also known as vProcs. Back to the architecture diagram then, where we will now turn our attention towards the in-database analytics feature. This is in fact related to the native object storage, since it allows us to query data that lies in an external platform. These queries are enabled by the advanced SQL engine, which, as discussed before, supports standard SQL operations, but also offers support for various ML-related tasks, including data preparation and model scoring. When analyzing large datasets, we may need the help of some advanced statistical tools, for which there is the Vantage Analytics library, which includes hypothesis testing functions as well as options for feature engineering. So we can use statistical tools for ML. On top of everything in the architecture diagram are the interfaces to actually work with Teradata. And beyond the APIs, a number of high-level languages are supported. The most commonly used languages when working with Teradata include SQL, and as touched upon, this goes beyond just regular SQL and includes analytics and ML operations. And then we can perform similar tasks using Python libraries as well as the R programming language. Now that we understand some of the significant features as well as the architecture of TeraData Vantage, let's explore some of its most common use cases. Before we get into the details though, let's take a look at how analysis operations have traditionally been performed. Here, data from an operational system such as a relational database is periodically migrated into a warehouse. The data that is migrated may include sales recorded at a retailer. Over time, as more and more data is migrated, the warehouse becomes the single source of truth in an organization. If the record of a sale exists in the warehouse, it means it did happen. Once we have a large enough volume of data, we can perform all kinds of analysis operations in order to gather useful insights. For example, perhaps the sales of a certain backpack spike up just before the summer season. Such insights can be useful when it comes to guiding business decisions. Sticking with our backpack sales example, perhaps a company can launch a marketing campaign in the peak season in order to vastly increase sales. This traditional approach has been applied for several years and quite successfully in the case of many companies. However, this does come with a few limitations, especially with regards to the rate at which data is being generated in recent times. In the traditional approach, there is usually a large lag between the data being generated and its analysis, and this lag could often be a few weeks or maybe even months, depending on the migration schedule. This means that if there are any new patterns which emerge in the data, companies will be rather slow to respond to them. For a retailer, if a certain product gains in popularity for only a handful of weeks, it may be too late to respond to that trend in the case of traditional analysis. Beyond that, the traditional approach often involved the maintenance of several data platforms, one for operational data and another one for analysis, among others, which means that the overall application environment is quite complex, since each platform may require their own set of hardware as well as their own networks. Furthermore, different skill sets will also be required for each of the platforms, which in turn adds to the complexity of hiring. On the other hand, if an organization were to adopt TeraData Vantage, they will be making use of an active data warehouse. In other words, a single store for both operational as well as historical data. And it's not like we need to flip a switch to go from carrying out transactions to performing analysis. Both of these types of operations can go on at the same time. And as we have touched upon a few times already, the SQL in TeraData Vantage goes beyond the standard SQL and includes several statistical and ML-based operations. With that said, let's take a look at how exactly an organization, specifically an e-commerce platform, may make use of TeraData Vantage for transaction analysis. Each new sale that is recorded will be stored as rows in one or more database tables. Once there are enough transactions to analyze, a clustering operation may segment all of the purchases into specific clusters, and these clusters may serve as a base for further analysis. This in turn might reveal that there are specific clothing brands that happen to be very popular in certain regions. It may be a combination of these brands and regions which make up some of the clusters. Based on this information, a company may decide to procure more of the products corresponding to those brands in the regions where they're very popular, while not changing anything in the other regions. Beyond that, there are several other use cases for TeraData Vantage as well. Its machine learning capabilities make it the ideal tool for fraud detection and prevention in financial institutions, where each transaction can be classified as legitimate or potentially suspicious. TeraData Vantage also finds utility in identifying traffic patterns in cities, and a good analyst may be able to suggest actions to improve congestion. Vantage may also be used to perform sentiment analysis on various text data, for example, on product reviews on an e-commerce platform. Vantage may also be used to study supply chain data in order to identify areas of optimization.